Hi, so I'm Randy Schaup still, and I'm the VP of Engineering at WeWork still. And Erez and Yael asked me to talk about an agile approach to machine learning. So I want to start with, I'm not even sure I would call myself an agile expert, and I'm certainly not an expert on machine learning. However, I have worked at 4 different companies where we've applied machine learning to our engineering practices and to our software. And so it turns out that once I thought about it, I did actually have a lot of thoughts on what are ways that we can make machine learning more successful and applying a bunch of the agile methodologies. But I will say that if you're going to ask me about the details of particular machine learning algorithms, I'm not the right person to ask about that. But there you go. Okay, so right now I'm VP of Engineering at WeWork. We have an office in Tel Aviv that's actually applying and building some of the technologies that I'm going to talk about at the end of this talk. Before that, I worked at a company called Stitch Fix in the United States. Stitch Fix is a clothing retailer, and one of the things that it's known for is a very, very heavy use of machine learning and data science to try to figure out what kinds of clothes people would like and send them those clothes through the mail. I also spent some time at eBay where we introduced machine learning to the ranking function for the search engine that I'm going to talk about later. And then Google has been doing machine learning at scale for quite a while. Okay. I've divided the talk into sort of 5 different sections. Basically, the different sections of things that we need to care about when we want to apply machine learning. And the first one is the problem, meaning what do we actually want to solve with machine learning or with our software? And so if I could ask you to take away just 7 words, if I could remember you to remember 7 words out of this presentation, I would ask you to remember these 7 words. What problem are you trying to solve? It turns out that this is a problem, this is a question that we can ask lots of times, but it's particularly important in the machine learning area because machine learning is a relatively new set of technologies, and because it can do lots of different things, we really, in order to be successful, we really want to have a particular idea of what we're trying to accomplish with machine learning, and only then can we make sure that we're actually going to accomplish it. So the way I might reframe this question for machine learning is this: agree on what you're optimizing. Agree on what you're optimizing. So every machine learning technique is some flavor of an optimization strategy to take a bunch of data and reach a particular result that you want. And it's very important for us, before we start on a machine learning journey, to figure out, not just with engineering, but also with product and business and other aspects of our company, to try to decide what is the criterion we're actually going to use to measure our success. Does it make sense? Because we could optimize for lots of different things, but it's important that we agree on something that actually matters to customers. So to be more specific, when I want to evaluate the success of a project or even decide whether to do it at all, I first want to decide on that optimization criterion. Or to use Ronnie Kohavi's term, Ronnie Kohavi built the experimentation platform at Microsoft, very, very well-known person in the sort of experimentation and data science space. So he likes to say that you need to define the overall evaluation criterion up front. We could also call that the optimization function. We could call that one metric that matters. But in all those ways, what we're talking about is what is the one kind of metric or one number that we're trying to optimize for. And one of the important things that we do is we should discuss and agree among the sort of engineering and data science part of our team, but also with product and business on what that thing actually is. And it's critically important that we not just choose a metric that's easy, but that we choose a metric that actually matters to customers, or as I like to say, is aligned with business value. So examples of not so good or better and not so good metrics is, let's imagine we are an e-commerce site or a search engine like Google. You actually want to optimize for the actions that you want people to take, purchases or something like that downstream, rather than click rate up front. Does it make sense? There are lots of ways to optimize for click rate that don't actually move the business forward. Similarly, for a business like ours at WeWork, our main optimization criterion for our team is long-term customer value. So through the entire life cycle of a customer being with us, how do we optimize to make sure that that long-term customer value is higher versus things that we could do to increase short-term revenue but might cause customers to churn later on. Does it make sense? Cool. And then again, Ronnie Kohavi's term, I really like this, is if you have a sort of funnel kind of process like hiring or like a search engine or something like that, the metrics that tend to work best for that are what he called the pirate metrics. And pirate is because it sounds like R and pirates say R. And so for those types of things, you want to optimize for things like acquisition, then activation, then retention, then revenue, and then referral. So that's what he means by pirate metrics. The other thing, of course, here is that we want to make sure that that optimization criterion is valid and measurable. And when I say valid, I mean not just chosen by a product person or a business person, but something that's validated as like statistically predictive of long-term success of our business. And the best people typically to do that are data scientists. Does it make sense what I'm saying? It's really easy for us as a business person or as an engineer to choose an easy metric that's measurable, but we need to make sure that we use data science to figure out whether that metric that we're trying to optimize for is actually predictive of future success. And actually with my team at WeWork right now, we're actively having those conversations, and my data science team is exactly telling us, oh no, this is a better metric than that metric, exactly because it's more predictive of that long-term customer value. And so obviously when we're trying to choose one of these metrics, we'd like to choose a metric that is predictive of future success, so maybe a leading indicator, if that makes sense, rather than a lagging indicator, something that would indicate success but not indicate that success happened in the past but not be predictive of it going forward. Okay, so this is helping to define the problem, where I mean the problem is what optimization criterion do we want to use for machine learning. Another reason to state the problem very well is this. So Charles Kettering used to head research at General Motors in the United States, and he liked to say this, that a problem well stated is a problem half solved. And for the engineers in the room, whenever we're given something that we need to do, hopefully one of the first things that we do is actually break down the problem into digestible chunks and understand the problem very deeply, because that way it's going to help us to figure out how to solve the problem. So the other reason to think about a problem statement or good formulation of a problem, particularly in machine learning, is this joke. I'm not sure if it's gonna land, but I'll explain it if it doesn't. This is from XKCD, which is a wonderfully geeky comic in the United States. It turns out that some problems are really easy to solve, and some problems are very, very difficult to solve. So the joke here is that finding out whether a person's location is in a United States national park or not is very easy, right? We just look up in some geographic system with our latitude and longitude, and it's very easy to find out whether we're in a national park or not. But then what the business person on the left doesn't realize is detecting whether there's a bird in the photo is actually a very, very difficult problem. And actually, I'll put a little asterisk by that, because when this joke was written maybe 5 or 6 years ago, identifying birds in pictures was a very difficult problem, and it was unsolved, and it was at the level of research, but now it's actually really easy. Okay. So that was talking about the problem, making sure that we formulate the problem correctly, aligned with the business, and in a way that we can solve it with machine learning. Next, I want to talk about data. And this is probably the most important section, because getting the data wrong means that nothing that happens downstream matters at all, right? If we don't have good data, it doesn't matter how fancy our algorithm is, it doesn't matter how fast our development process is, the data is really the core thing that allows us to move forward. So the first thing that we want to do is, I'll call it characterizing the data. I've worked at a bunch of different companies, and at Google in the search engine, that's big data, but it's very shallow. Does it make sense what I'm saying? You can collect billions upon billions of individual events every day, but each one of those individual events is not very interesting. They're only interesting in aggregate. Does it make sense what I'm saying? Big and shallow. But by contrast, there are other sets of problems that are what I'll call small data, but really deep. So at Stitch Fix, again, we were collecting data about about customer preferences with clothing. So we would send a box to our customers with 5 items in it, and they would keep some of those things and return other things. That is a very small amount of data because we're maybe only sending a box to a customer every couple of weeks or every couple of months. So it's a very small amount of data, but each one of those individual decisions, whether one of our customers keeps a piece of clothing or whether she sends it back, is hugely powerful and hugely predictive. Does it make sense what I'm saying? That's small but deep. And the techniques that we're going to use in the big and shallow case are going to be very different from the techniques that we use in the sort of small but deep case. Okay. More generally, it is universally true in machine learning that better data is going to beat a smarter algorithm. So what do I mean by that? I mean that if I have more data, if I have more accurate data, if I have more predictive data, if I have cleaner data, I'm going to be able to beat the other person, even if that other person has many, many PhDs with machine learning working for them and having a much fancier algorithm. Why is that true? It's because it turns out that all the algorithms scale, their accuracy scales much better with the amount of data that we have. So when I say better data, I mean a bunch of different aspects of better. So the first part is I need the data to be clean. And as we'll see in a few moments, the vast majority of the time spent in data science and machine learning work is not about coming up with a fancier algorithm. That's a tiny percentage of a typical machine learning person's work. The vast majority of it is getting the data into a form that we can insert it or apply the algorithm to. So cleaning up the data, it turns out, it seems like that should be trivial and that should be a very small amount of our work, but it turns out it's actually a very large percentage of it. So the next thing that once we have clean data, in other words, once we've removed, once we've figured out, data that's missing or data that's only partially there or data that's incorrect, once we have a bunch of data that's clean, now we need to aggregate it together. And in particular, what I mean is most machine learning algorithms will run on conceptually a single data set, right? We pass a single data set into whatever algorithm, and then it's going to give us some results at the end of that. But it turns out that a bunch of those pieces of data tend to come from different sources in our enterprise. And so one of the things we need to do is we need to join those things together, consolidate it into one at least logical table, and aggregate it together so that we can feed it into the algorithm. The next thing, as I'm sure people are familiar with, is the idea of labeling. Who's heard of labeling data? Wow, okay, not enough, but that's cool. I'm glad I'm describing it then. So labeling is the process of asking a human whether the prediction that we might make is successful or not. Typically in most machine learning things, we need to learn. And the only way that we can learn is knowing when something is, correct or incorrect. So if we have like a classification problem, like we want to decide between cats and dogs. So let's imagine our problem is, given an image, decide whether that image contains a cat or contains a dog. Okay. The only way that we can do that is by asking a human, to start out with, asking a human for a set of images, is this a cat or is this a dog? Does it make sense? That's called labeling. And we need labeled data in order to use any kind of supervised algorithm. And most of the algorithms that we use are what's called supervised, where we know the correct answer for a certain set of training data, and we use that, we train a model on that, and we use that to infer whether something's a cat or a dog on new experimental data. So it's very, very important to label things. And it turns out, again, because this involves humans, that in lots of situations, it's actually really hard to scale the amount of labeling. Does it make sense what I'm saying? Cool. All right. So the next aspect of better data is simply more. So once I have clean data, it's aggregated and it's labeled, now I want to acquire more and more data. And typically there will be some feedback loop where somebody who's trying to build a model says, oh well, if I had more attributes about this particular event, I could be more predictive. So great, more data is going to be better. Okay, cool. And then the last thing I would say here is timely data. So getting the data from the operational systems, the production systems, into whatever offline area you're using for training, being able to do that in a small amount of time rather than a larger amount of time. Okay, so as I mentioned, we might have an intuition about what data scientists and machine learning people do, and it's coming up with fancier algorithms. It turns out that's a very, very small percentage of that. In this example with Crowdflower, it's only 4% of a typical data scientist time is spent on refining algorithms. The vast majority, so almost 80%, is spent cleaning and organizing data. That's 60% here, and then the 19% is collecting the data sets together. Does that make sense? So if you're about to embark on something like this, recognize you're going to need to spend a lot of time, particularly when you're doing it first, cleaning up and aggregating the data in a way that's useful for your algorithm. Okay, cool. So the next set of things I want to talk about is the algorithms. And so from an agile perspective, as always, we want to start small and get something out and working, and only later do we get fancier. So the typical evolution of algorithms is it starts by doing something that we write very explicitly in code. So we might write rules, or the fancy term is heuristics, where we do a bunch of maybe if this, if that, then that. Does it make sense? So if I want to recommend, in our case, we recommend rooms for people to book. We might write a simple rule that says, if somebody's booked this room more than 3 times, put it at the top. Does it make sense what I'm saying? There's no machine learning in that, but that's an initial way that we start to solve the problem. So then the next technique typically is we start to use pretty simple algorithms. So not yet something really fancy or really complicated, but maybe something very simple like regression or decision trees, or even something like collaborative filtering, like people who like this might also like that. And you might be able to be done here. Again, with Agile, and because we've had that optimization criterion that we determined, we might be able to do a really good job even with a very simple algorithm. And then, only if the simple algorithm isn't good enough, or if we want to get even better, we might apply more advanced techniques like dynamic programming, iterative optimization, fancier techniques like neural nets and deep learning. Does it make sense what I'm saying? Start small, very simply, and only later get fancier and fancier. And then the last thing I would say is typically once you're beyond applying one fancy approach is you can use an ensemble or a portfolio of approaches, and together use that to make the prediction. And people maybe are familiar with the Netflix prize. This was about 10 or 12 years ago, where Netflix offered a $1 million prize to anybody out in the industry that could beat their recommendation algorithms, beat the accuracy of them. And it turned out that all the winners tended to be these ensemble approaches that actually combined a bunch of different machine learned techniques to make the prediction. Okay, the process here is typically we see some usage in production, we collect the data, we're going to train a new model, and then we're going to deploy that model, and we go round and round, improving getting more data and deploying new versions of the model. So this is a feedback loop, just like in Agile or DevOps. There's a broader feedback loop, which is trying to improve the model overall. So starting with that model execution, we might take data into some offline way, have a data scientist try out new versions of the model, maybe fancier algorithmic techniques, different hyperparameters, and then deploy that model back to production. Does it make sense? There's an online feedback loop and also an offline one. Okay, great. The last thing I want to talk about in this section is about how to scale the development of algorithms. So one thing that I think is quite underappreciated about machine learning is that a bunch of the algorithms are very powerful, but they are not very interpretable. So a neural net can produce us a response, can say, oh, this is a cat or this is a dog, but we can't look inside the neural net, or it's very difficult for us to look inside the neural net and understand why it decided that. Does it make sense? But there are techniques that are maybe less accurate and less predictive, but are easily explainable. So those like linear regression, which we probably learned in statistics in school, but also techniques like decision trees or decision forests, which are essentially a fancy way to do if then else. You can actually look and understand exactly why the model made a prediction or didn't make a prediction. And the reason why I say interpretability or explainability is important is because when the thing makes a bad prediction, or when you want to improve the algorithm, now you know where to look. Does it make sense? By being able to interpret why it made a particular decision, now you can figure out how to improve it. The other approach is, or another thing that's really important, which we did at Stitch Fix, is something that I'll call DevOps for data scientists, where where just like you would empower your engineers with a common platform, that they can move faster in their individual teams. Similarly for the data scientists, where one of the teams that I'll talk about in a moment provided a broad platform for algorithmic development that made the data scientists much more autonomous and much more able to move quickly. And again, as I mentioned, that algorithms platform is a way that helped the data scientists to be more independent and more productive. So the example that I'll offer here is an example from that company Stitch Fix. And there was a team, just like you'd imagine a software infrastructure team or a DevOps team, even though I hate that word. You can imagine a similar team for the data scientists that provided a platform that allowed the data scientists to do their work in a way that made sense to them. So the next thing I want to talk about is experimentation. And I love this quote from Richard Feynman, so Nobel Prize winner. It doesn't matter how beautiful our theory is, and it doesn't matter how smart we are. If the thing that we think that we do doesn't agree with an experiment, it's wrong. So let's talk about designing and running experiments. So the first thing when we run an experiment, whether we're in science or we're in industry, is we want to state our hypothesis. We want to say, if we change the color of the background of the page from red to blue, we think that people are going to click more. Like, we need to have some kind of hypothesis that we can actually test. Then we need to design what's called an A/B test. So at the same time, we show people with the red background and other users with the blue background, and we monitor the business metrics of the red cohort and the red group and the blue group. We want to I call it obsessively log and measure, because not only because we want to understand that the red was better than the blue or the blue was better than the red, but we want to be able to understand why. Well, how is the system behaving? How are the users behaving? And so that logging and measurement allows us to take learnings back from that experiment and help us design new experiments going forward. And then the final thing, and I think Kevin said this very well in the morning keynote, is listen to the data. The data is going to trump, the actual data of how things are actually behaving trumps any of our opinions or any of our intuition. And then the last thing is rinse and repeat, right? So we've designed one experiment with a hypothesis and an A/B test and a set of learnings, and then we design the next one and the next one and the next one. One of the great things that Ronnie Kohavi learned as he was running that experimentation platform at Microsoft is this idea that 1/3 of the ideas that they had were positive and actually moved the needle in a statistically significant way. So this is actually pretty successful. 1/3 of the new features that they tried at Microsoft worked. Turns out that 1/3 of them actually moved the needle in the negative direction, and 1/3 of the ideas were flat. So imagine if they were not doing this in an experimental way with statistically significant results. They would have no idea whether they were doing something that was improving things, something that was making no difference, or something that was making things negative. Does it make sense what I'm saying? Most of us do this stuff, pull out new features without even measuring. And so the important thing is to actually measure. Because again, maybe only 1/3 of our ideas are going to be great. Cool. The other thing, of course, about learning is, again, a wonderful quote from Feynman. Being wrong is not a bad thing. In other words, oh, I thought that the blue background was going to make things better, and it turns out it actually made it worse. But being wrong isn't bad. It's an opportunity for us to learn. And if we can understand why the blue made the difference in the negative direction, maybe we can design a better experiment going forward. Does it make sense? Cool. Great. So two other things that I'll kind of connect this up in terms of Agile. One of the things is it's very important for the effectiveness of a machine learning idea to have continuous delivery. So have a repeatable deployment pipeline, as other people at this conference are talking about, being able to release things in smaller units of work so we can do very small experiments very rapidly. And this very directly, simply by being able to do continuous delivery, it allows us to experiment on more things and learn things more quickly. So the other aspect, how we do this in practice, is people have probably heard of this idea of feature flags. So this is a configuration of whether a feature is on or off. And we can also apply the same technique to experiments. So we might have a flag that says which people are in the red background group and which people are in the blue background group. And the feature flags allow us to make us move quickly, and it makes us moving quickly safer, because if anything goes wrong, we can just turn the entire experiment off. Does it make sense? And again, this enables experimentation because it allows us to move quickly, safely, but it also gives us a way to configure whether somebody is in the experiment group or the treatment group. And it also gives us the ability to turn the experiment on and off very easily. So 2 quick examples from eBay when I was there. So one of the things that we did was introduce the concept of machine learning to the search ranking function. So people might be familiar with a ranking function for search. That's the thing that scores the results and decides what thing goes in the first position or the second position or the 10th position. So our intuition was that we started from like one of those heuristic or rules-based things with a very small number of factors, but our intuition was that if we used hundreds or thousands of factors in a machine learned model, we would actually be able to make better ranking decisions. So for a year, we tried hundreds of parallel A/B tests at the same time, and after a full year of making tiny little progress, tiny progress, tiny progress, most of which, by the way, were not successful, back to Ronnie Kohavi's idea, we got this after the end of a year. We were able to increase the overall revenue of the eBay company by 2%, so it actually earned us $120 million US every year. At the same time we were doing this experiment, we were also doing separate sets of experiments on simply making the search pages faster. So our hypothesis was that if we made the search pages faster, people would buy more. And so again, we went through an iterative process of making minor improvements to the search pages to make them faster and faster. And again, we got another 2% increase in the overall revenue of eBay. So if I add those 2 things together, we basically added $240 million or $250 million to eBay's bottom line simply by these 2 small sets of experimentation. Does that make sense? Pretty cool. The last thing I want to say here in terms of experimentation is this idea about the Hippo. Has anybody heard? Hippo is again coined by Ronnie Kohavi, is the highest paid person's opinion. The highest paid person's opinion. So one of the big risks to doing experimentation and driving things from data is the idea that, oh no, we should just ask the big boss and she's going to tell us the right answer. Does that make sense? Yeah, okay. It also turns out that hippos in real life are the most dangerous animals, like not lions or anything like that, it's the hippos. Anyway, all right, cool. So in the last section, I want to kind of put it all together, and I'm going to use a bunch of active projects that we have going at WeWork to talk about how we can do these things at scale. So the first thing, which actually my team here, or the team here in Tel Aviv has contributed to very significantly, is the idea of making recommendations for events in our spaces. So we organize a lot of events for the people for the members of our co-working spaces, and so one of the things that we do is we've asked people to give us to share with us some skills and interests that they have. We've developed a predictive model associated with that, and so we can predict which people might attend which events, and we recommend those events to those people. That's the recommendation to the member side. There's another side, which is where we can recommend to our community managers, the people that design and host those events, what are new kinds of events that people might like in your building based on their skills and interests, and also we can give them a whole recipe about what makes a successful event. Does it make sense what I'm saying? So very directly, even in what would seem like a not machine learning place like a co-working space, machine learning is very applicable. So other aspects, we have another team that works on predicting occupancy of new buildings. So when we want to open a new building, we want to make sure that it's going to be occupied. We can also use that same set of things to simulate revenue when we open a new building and in our existing buildings. We can price the offices based on the particular attributes. Does it have a window? Is it a corner? That type of thing. We can use it to manage our inventory. And last but not least, I love this animated GIF here, we can actually use it to automate the layout of new buildings. So we have a new floor, and we use algorithmic techniques to, we say where the walls are, and you can see that it's actually filling in where the desks might be based on some constraints about how that works. Does it make sense? Cool. Well, I'm out of time, so I hope this was useful. So we talked about the problem defining the problem about what we would want to solve with machine learning. We talked about how to get data. We talked about how we might iterate on the algorithm, and we talked about how we'll do experimentation. So, toda.